Hello, everyone, and thank you for coming to my talk. I'm Harapati Mata from Harvard University, and I will be talking about contextual search in the presence of irrational agents, which is my joint work with Akshay Krishnamurthy, Theodoris Likouris, and Robert Shapire that we started when Theodoris and I were both at Microsoft Research New York. So contextual search or feature-based dynamic pricing problems are actually very prevalent in real life. As an example, the smart pricing algorithm that Airbnb uses in order to suggest prices to superhosts can be thought of an example of a feature-based dynamic pricing problem. In a stylized modeling, there's a product that arrives with a number of features. These include the location, the number of rooms, and so on and so forth. Then Airbnb, based on these features, gets to suggest a price. The user, seeing this price, decides to purchase or not, and Airbnb observes the feedback, which is whether the purchase happened, and gets to collect the revenue from this interaction. Now, the goal from the side of Airbnb or the platform is to set prices or suggest prices in order to collect as much revenue as possible. And to put all these things into a slightly more mathematical perspective, in this talk, we will be talking about an interaction between nature and a learner. In the beginning of the round, nature chooses a d-dimensional context xt. This is observed by the learner, but is also chosen adversarially by nature. The learner, after observing xt, gets to choose a price pt, which is a scalar. This is presented to the user, who then decides to purchase or not. Now, the user decides whether to purchase or not as follows. They decide to buy only if the context valuation is above the price. And this mathematically is xt.theta star above pt. So there's this linear dependence between xt and theta star, where theta star is a common feature value across all rounds and across all agents. Then Airbnb gets to observe the feedback, which is essentially the binary feedback of whether xt.theta star was above or below pt. And then Airbnb collects revenue, which is the price pt that was suggested if a purchase occurred, otherwise it's zero. And in this more mathematical terminology, we will want to minimize regret, which is the difference between the total revenue for a benchmark pricing policy minus the total revenue collected by our algorithm. And the benchmark pricing policy is basically what you would have done had you known theta star. Now, I'd like to note that so far, I've mostly described the problem of feature-based dynamic pricing, but in fact, this model can encapsulate the bigger family of problems known as contextual search, where everything up until step four is the same, but what differs is the loss functions that we use in order to measure how close was the learner's query point from the ground truth, which is what would have happened if the learner knew theta star a priori. So in all of these problems so far, there has been a key behavioral model assumption that people have used. We call this assumption full rationality in this work. And it basically is that the agent buys if and only if the context valuation is above the price. But you can imagine that in many cases, when especially we talk about like real life examples, agents may wish to deviate from the prescribed behavioral model. And in this work, we will be thinking about these deviations from the prescribed behavioral model as irrationalities. So for example, agents may decide not to buy, even if the price is below their valuation, due to the current psychological state that they have. Now, the problem is that even if you have created optimal learning algorithms against fully rational agents, if you were to encounter even a few model misspecifications, these can cause arbitrary failures to the standard optimal algorithms that we know of. So the main question that we address in this work is how do we get to design contextual search algorithms that are robust to the presence of some irrational agents? And as a reminder, when we talk about irrational agents in this work, we essentially talk about mean agents that deviate from the prescribed behavioral model. So for the fully rational case, there has been a series of works, great papers that have appeared in EC and Fox and Soda, for the setting that I described earlier, as a reminder, the nature chooses an observable context xt, the learner gets to select a price, the agent makes a purchase if xt.theta star is above pt, the learner observes this one-sided feedback and collects the revenue. I'd like to point out that when we talk about one-sided feedback in this work, here's what we mean. If the learner were to query price point 2 and the agent buys at this price, then the learner also knows that the agent would have bought for any price below O2, but has absolutely no information about what would have happened for prices above O2. So that's where the one-sided feedback comes from. So for this contextual pricing problems for fully rational agents, the regret that has been known is big O D log T, and the benchmark pricing policy is essentially xt.theta star. This is the policy that we are competing against. Now, I'd like to point out that this regret guarantee that I present here is not the optimal for all the losses that are considered within the broad family of contextual search problems. We will be using this regret guarantee because it generalizes well to many losses, but there have been better regret guarantees obtained. In fact, for the revenue objective, the recent paper of Liu, Pais, Lemma, and Schneider in SOTA 2021 achieves the optimal guarantee of big O D log T. And we know that it is optimal because for the single dimensional case, we know that this is the optimal solution, which is due to Kleinberg and Layton in their seminal paper of FOX 03. So one of our first contributions in this work is to start thinking about adversarially irrational agents through the use of the corruptions framework that has recently gained a lot of interest in the machine learning community. So now at each round, nature chooses the observable context xt, but also decides on the binary corruption for this round, ct. Ct is equal to 1 means that this is going to be a corrupted round. This is going to be an adversarially irrational agent. Ct0 means that this is going to be a fully rational agent. The learner gets to select a price after they observe the context, but having no information about the corruption of the current round. They present this price to the agent, and then the agent, makes a purchase if xt.theta star is above pt, if ct is equal to 0, meaning that if ct is equal to 0, then the agent behaves according to the linear behavioral model, but the agent behaves completely arbitrarily if ct is equal to 1. The learner gets to observe if a purchase occurred, which could have been because of an arbitrary behavior, or it could have been because the current round, this is exactly what the linear behavioral model says. And then the learner collects the revenue if the purchase occurred. Now, if we denote by capital C the total number of corruptions throughout the rounds, the two desiderata for our algorithms will be to first achieve a graceful degradation of the regret with respect to C, the total number of corrupted or adversarially irrational agents that we encounter. And two, we will want to achieve this graceful degradation without assuming any knowledge of C. We will be calling these algorithms that are agnostic to C. Now, you can imagine that when we talk about pricing settings and adversarially irrational agents, it would be far-fetched to assume that the learner has knowledge about how big C is. So the main result that we present in this work is a robust contextual search algorithm that is agnostic to C and achieves regret guarantee big O C D cubed log T cubed with high probability. And I'd like to point out that if you remember, the regret guarantee that I showed you for the non-robust case, for the fully rational case, was D log T. So we end up having an overhead of C D squared log D squared. The other thing that I'd like to point out is that our result essentially extends the classical Ulam's game in two ways. First, it is multi-dimensional version of this problem. Ulam's game is a single dimensional problem. And it is also agnostic to C. So in Ulam's game, the number of lies is assumed to be known. Now, in the classical Ulam's game, we are talking about like a single dimensional binary search setting where the learner interacts with an adversary who has, the learner queries points, and then the adversary response if the queried point is above or below a target point that they have in mind. And the extra thing is that they have a total number of lies that they can use in order to try and fool the learner. And in a paper of Rivest et al. From 1980, it was shown that there exists a tight bound for this problem of log t plus c log c plus c log t. Okay, so before I start building on the techniques that we used in this work, let me just walk you through at a high level of the non-robust algorithm of Lobel, Paislem, and Vladu that we base a lot of our analysis on. So this algorithm should be thought of as a version of a multidimensional binary search procedure, and essentially gets a lot of intuition from cutting plane algorithms. At each round, the learner maintains an active knowledge set with all the feasible values for theta star. You should think of this as the version space for theta star. Then the learner gets to observe the current context and queries the price, which is centroid of the knowledge set, inner product with the observed context. And then once the learner queries this price, after they receive the feedback, they get to eliminate the inconsistent side of the knowledge set. How is this done? This is done through hyperplane cuts that are perpendicular to the context. So if, for example, you are to query point x1.kappa1 that passes through the centroid, then you know that for all values theta, such that x1.theta is less than x1.kappa1, basically all of these values of theta here, you know that a purchase wouldn't have happened because it's on the opposite side of theta star. So you should maintain this side of the knowledge set, and here exactly that's how you make the cut. Another example, if this is the next context that you receive, and this is the queried hyperplane essentially, then you end up making cutting off this space here because it's inconsistent with where theta star lies, and this is how you keep going about minimizing your version space. This algorithm, as a reminder, achieves a regret of big O D log D. There have been two important properties of the context cut that I've been describing. One is that you never get to eliminate theta star. And this is kind of easy to see because you always see feedback that is not altered from lies. The second property is that you make enough volumetric progress at each round, meaning that by cutting parts of the knowledge set through these hyperplane cuts, you end to shrink the knowledge set enough at each round so that you end up at some point with a knowledge set that is very small around theta star. So what is the issue if we try to apply this type of algorithm, a multidimensional binary search type of algorithm, for adversarially irrational agents? So to answer this question, we're going to be thinking about the simplest version, the binary search, which is for d equals 1. So the question that I ask you is, if I fix a number theta star, how many queries do you need in order to find it with accuracy epsilon? And I will always promise to respond truthfully. So what would you do? Well, you would start by always querying the midpoint. If you query 0.5, I'll tell you that it's on the right side. So keep this interval. Then I tell you that, then you query 0.75. So I tell you it's still on the right. And so on and so forth. You end up with an interval that's epsilon close to the actual theta star. Now, what would happen if I told you that one of my responses is going to be corrupted? I don't tell you which response is corrupted, however. Let's see what would have happened after log 1 over epsilon rounds. So you query 0.5, and I decide that this is the response that I'm going to corrupt. So I tell you that, oh, the theta star is on the left-hand side of this query point. So you keep going with your log 1 over epsilon queries, and I respond truthfully ever after. So you end up having this interval here, which is very far away from the actual theta star. And this can be detrimental for pricing settings because you lose a ton of revenue by not caring about the fact that you see one response that is corrupted. Now, one idea would have been to repeat each query multiple times in order to be sure that once you eliminate part of the knowledge set of the version space, you are safe. So you have eliminated something that was not corrupted. And keep this in mind, keep this idea in mind, because this is this is one of the key ideas that we will need for the contextual version of our problem. So for now, let's focus on the following challenge. How can we fix the existence of corruptions in contextual settings when we know that C bar of the responses that we will receive are corrupted? This is a strictly easier version compared to the one that I promised that I will be solving in this paper, which is the agnostic to C, agnostic to the number of corruptions. But we will focus on the known corruption case first, and I will explain the unknown corruption case at the end of this talk. So, okay, what did I tell you to keep in mind? Keep in mind the repetition of the queries. So the first challenge that we encounter in contextual settings is that we cannot repeat the same query. And that is because contexts are different at different rounds. So remember that contexts are chosen adversarially by nature. So if you were to, just to give you like a pictorial view, if you were to create contextual cuts, which are essentially hyperplanes that are perpendicular to the context, these can be arbitrarily different at different rounds. So the first idea for dealing with this is to keep a penalty for each of the parameters of the version space and make a cut in the version space only once a context cut fully retains the protected region on one side. And the protected region is the region of the version space that contains all the parameters that have penalty at most C bar. Now, why did we pick this protected region? Well, if you know that C bar of the responses are going to be corrupted, then you know for a fact that if you keep all the parameters that have suffered at most C bar corruptions, then theta star, which is the target parameter, is for sure part of this knowledge set that you have kept. Great. So the next challenge that we face is that you may never have a context cut with a protected region fully on one side. What do I mean by that? If you are to collect time steps and create an epoch and wait for this epoch to have enough contexts in order to guarantee that one of the context cuts has the protected region fully on one side, then you're doomed to fail. In fact, in the paper, we show a counterexample where even if you have an infinite number of contexts during an epoch and the number of corruptions is 1, then it may be the case that no such context cut exists. This is a byproduct of the fact that contexts, again, are chosen by nature adversarially. So the idea, our next idea would be to somehow combine context cuts in order to compute what we call a valid cut. And a valid cut has two important properties. It first never eliminates theta star, meaning that it fully protects the protected region. And two, it makes enough volumetric progress for us to guarantee that at some point we're going to end up with a knowledge set with a version space around theta star that's actually small. Now, the question that arises is that, okay, can you guarantee that after you have a number of context cuts, that you have actually a valid cut? And are there any extra assumptions that you need in order to satisfy that? The answer is that you don't need any extra assumptions. And after 2D D+1 C bar plus 1 context cuts, in fact, you have enough information to compute a valid cut. And this is given to us through Kara-Theodoris theorem. And just to give you like the high level idea of why this is the case, if this is your current version space, and this is theta star that you wish to identify, and this is your current protected region, which observe it is a non-convex set. It's actually a union of convex sets. Then what you know is because you know that all of these points here have a penalty at most C bar, then for all the black points that belong in the convex hull of this protected region, you can actually write them as at most D+1 points from the non-convex region. And this is enough to guarantee that you can correlate the penalty of the black points with the penalty of the points in the protected region. So great, now you have a convex set, this convex hull, that you know a property, which is that the penalty is below, I'm sorry, an upper bound. So the final idea for our work is to identify a point in the knowledge set that has penalty larger than this convex hull, because this is enough to guarantee that this is outside of the convex hull. And then just use perceptron algorithm in order to separate this point from the convex hull. So in fact, we do not use perceptron directly. We use perceptron as a witness for finding a valid cut. So the standard perceptron algorithm says that if you are given points from two classes, one with label -1, one with label +1, that are separated by a margin gamma, then you can identify a maximum margin separating hyperplane after at most big O 1 over gamma mistakes, which in our case translates to the following. If we knew exactly the green point and the convex hull, and these two classes had enough of a margin, then we could run perceptron and be done with it. And I can tell you that we can identify such a green point which is outside the convex hull in polynomial time. And let's assume for now that the convex hull is known to you. Now, the problem that arises is that they still do not have enough margin. So it can be the case that perceptron never finishes. So here's what we do. We sample randomly from a ball around the green point, which remember, we can identify. And then from geometric, from convex geometry arguments, we know that with constant probability, we will end up sampling a point from this patterned region. Now, why is this enough? Because if we have finally sampled a point from the patterned region that does have enough of a margin, then perceptron will terminate deterministically with at most 1 over gamma squared mistakes. If the data set is not correct, then we need to resample. And we know that this process will terminate. Why? Because we have proven the existence of a good separating a valid cut in the previous slide. So that was all an idea about how we deal with the known corruptions case. So let me just say a word about what we do about the unknown corruptions case, where we essentially create an extension of the multi-layering race technique of Likouris, Mirokni, Paes-Lemma of STOC 2018 for continuous action spaces. We use, again, we actually change the two main ideas that they had in that paper, which is the subsampling idea and the global eliminations idea, this time for continuous action spaces. Here's how this looks for continuous action spaces. You still have log T layers. Each layer L will correspond to a different corruption level. So this layer, for example, corresponds to corruption 2, corresponds to corruption 4, and so on and so forth. You're going to sample a layer L to play with probability 2 to the minus L, meaning that layers that have higher index actually are played less often than layers that have smaller index. But the added benefit is that these layers are way more robust. So they can help inform the choices that the previous layers, the fast layers, make. And that's where the global eliminations comes into play. So if, for example, at some point T2, you end up sampling layer L2, and this layer tells you that, oh, if the knowledge set that you should maintain from now on is this thing here. So you shouldn't keep the whole ellipsoid, you should keep the half of it. Then it informs the previous layer, which was not as robust, and it cuts half of the space. Now, if at some point T3, the even more robust layer L equals 3 says that, no, you're both wrong, you should have kept this part of the ellipsoid, then this means that you should essentially create empty sets for the knowledge sets of the previous rounds. And any time that you are called to sample from them, just sample randomly from the right next correct layer that has a non-empty set. So very briefly, in summary, we presented the feature-based dynamic pricing algorithm with adversarial irrational agents, our regret guarantee has an overhead of c d squared log t squared compared to the non-robust version of the problem. There were 4 key techniques that we used in order to derive our bounds for the known corruptions case. And we used finally a variant of the multi-layering race technique in order to run parallel versions using c bar equals log t. And one more word about the paper, we also have analysis about bounded rational agents, so that do not fully satisfy full rationality. And we also have analysis about a gradient descent-based algorithm for contextual search. Thank you very much. And please feel free to ask me any questions or stop by my poster for more. Thank you.